And if you want to go from your laptop into this analog system, for instance, to do some filtering, you will have to increase the level of your signal. Now, I don't know if there's somebody that just happens to have a iPod or something, or laptop or MP3 player around. Okay, this is the oscillator level. This is the line level. But now if I open this gain knob, now I can do a funny trick, because I can take this as an output signal on the secondary output, which removes it from the crossfade mix, because now I'm sort of like in ducking mode, but I insert it into the pitch modulation of the oscillator. Without boosting the gain, almost no effect, but then okay. So that is just a very quick example of that it's absolutely easy to connect other instruments to the system. We actually have 3 points where we can do this, because we have the secondary inputs of the 2 faders, so that's 2 points. And in the left matrix, in the node processors of the left matrix, there's also a gain pot, which will have the same function. So you can insert a signal into the A2 in, and insert a signal into the B2 in, and insert a signal into the matrix. Use a stereo cable on the gain and open this gain, and connect 3 external line level devices to the system, and do filtering and all sorts of funny stuff to it. The way how this choosing between crossfading and panning, etc., works is, well, you see that in practice it's quite simple. If you connect only to the left input and you use both outputs, it's panning. If you connect to both inputs and only to one output, it's crossfading. If you connect to both inputs and both outputs, it's ducking. And then there's a 4th option. That is, if you connect to one input and one output. Now, if that one input is an oscillator, and that one output is the left channel or the right channel, doesn't matter. Well, it's the left channel, then basically you hear the signal all the time, but in the middle position it's a bit louder. It is actually 3 dB louder. And that is because if you do crossfade mixing or you do panning, the mixer curves are not linear, but they are actually so-called RMS, root mean square curves, or so-called equal loudness curves. And the reason is because if you add waveforms to each other, waveforms stretch over time, behave differently to singular numbers, in a way that you always have to sort of look at the average energy that is present over the amount of time that a waveform is there. And this averaging, because it's based on sine waves, is not completely linear. So it means that if you want to have a mix of 2 sounds an equal mix of two sounds that sounds to the ear equally loud as one single sound, one of those two sounds, then the mix is not a half times sound 1 plus a half times sound 2, which would be mathematically for a single number be the case, but it's actually 0.7 times signal 1 and 0.7 times signal 2, because it's not really numbers that you add, but you add basically the surfaces of the waveforms added and over time and sort of equaled out over time. And they call that so-called root mean square. That means that if you have sort of like a linear crossfader that you would make with two linear VCAs, and you would, or actually a panner, and you would pan from the left to the right channel, it would appear that the sound in the middle is much less than when the sound is at either of the two speakers, which in the studio they call the hole in the middle. So if you have a pen knob on a mixing desk, these pen knobs on a mixing desk, they always also follow this so-called root mean square behavior. So in the middle it's always 0.7 times one signal plus 0.7 times the other signal, left and right. That 0.7 is what they call 3 dB. And if you have the signal, in this case, here in the middle, it's actually 3 dB louder as when it's here or when it's here. But now you can do an interesting trick, because I can actually connect it to the second input, which means that now to the left I have silence, to the right I have a sound, and now effectively I basically have a VCA, because I can still modulate this. But this VCA now has a root mean square curve instead of the usual exponential of linear curve. So I can try if I can demonstrate the difference between one and the other, because I can use this signal and use this VCA, and one VCA goes to one, the other goes to the other. Now I need modulation signals. So I take an envelope signal. In this case, that you hear that the signal is present for quite a while, but now I use it in the other VCA, and the decay is much more immediate. Which sounds more snappy, like with more echo. And here it's much longer there. So in the system, we actually have several VCAs scattered all over the place, and we have VCAs with a so-called exponential curve, which are the most commonly used, which are into the filters. We have strictly linear VCAs in this node procession and in this node procession, and we have root mean square VCAs, two of them basically in the dual fader. So there's plenty of choices to make, and these things, if you just listen to them like we just did, you think like, wow, does this really make a difference? You know, it's not really that much. But the moment when you have other sounds, and the sounds come in contrast with other sounds, then the difference becomes much more obvious. So you always have to test this out. Like for instance, if a sound sounds a bit thin compared to other sounds, you can actually try to use a root mean square VCA. But if the sound is too long, too much there compared to the other sound, you can try to use an exponential VCA instead. So that's how it works. Now, there's even more variations that you can do with crossfading and panning and voltage controlled faders. And that is, imagine that you crossfade between a signal and an inverted copy of that signal. Basically what you do then is a ring modulation. That is also possible, and you can do that with this switch. The way it works is that you take one signal, and that signal you just put into, for instance, input A1. But we don't listen to the output of the first fader, we actually listen to the output of the second fader. Because I can route the output of the first fader into the inputs of the second fader, and with the switch that I have here you can switch between three possible options. And now I put the switch down so that it is in so-called ring modulation, and I can set the level that feeds in there here, and you can hear that in the middle position it's silent. And if I now carefully set it in the middle position where it is silent, I can add a modulation signal, another sine wave oscillator, to the modulation input. And then if I listen to that one and open the modulation knob, then you hear that we basically get ring modulation. But there's one interesting thing, because this is not linear ring modulation, because the curve is not linear. The curve is an RMS curve, which is basically sort of a compressive curve. That means that it's sort of, this ring modulation adds a sort of saturation distortion to the sound, which is very similar to the ring modulators that were used in the 50s and 60s, where they would not use like transistors and chips, but they would actually use transformers and germanium diodes to make these ring modulators, the kind of ring modulators that were used by people like Klaus, now like Stockhausen and so if you would like to recreate this kind of ring modulation sound from this Stockhausen stuff, which sometimes is quite beautiful actually, it is interesting to do that with this dual fader ring modulation, because it will give you that kind of thing. I think I can actually demonstrate it, because if I take a triangle wave, maybe take it from here. Now, the triangle wave has a small peak, so that means it is brighter than a sine wave. But you can hear that if I open the modulation amount, you actually lose a bit of that brightness that you have here. Because now the triangle wave gets sort of compressed at the tops. But if I do that with a sine wave, maybe this one, you actually hear that if you open it, instead of losing that brightness, you get a bit of extra brightness, because a sine wave is the dullest sound there is, so any distortion you do to a sine wave will give brightness. So that is exactly what did happen in these old transformer and germanium diode ring modulators from way back, and is sort of a thing that is, well, quite typical to this 50s and early 60s electronic music from that era. Of course, you can also do this with your iPhone, iPad, and use this gain controller and ring modulate an audio recording that you made of something else, or an instrument, another instrument that you put there. So you can sort of quite instantly use that technique. Well, I hope that explains a bit about the dual fader and about voltage controlled mixing, and also that basically using a voltage controlled fader this way is easier to work with than using a whole set of separate VCAs with a whole set of different control voltages. That's basically why it's there.
Curious about the third setting now.
Well, basically, if you want to mix 3 or 4 signals, you can sort of use these knobs to set the way how the second how the second fader behaves in the total mix, which means that you can sort of do it in a way that here you mix between A and B, and here you mix between A, B, and C. Or you can do it in a way that here you mix between A and B, and you set the level of A and B here on the output, and here you mix between C and D. And you can also sort of close the C input in this case, which in some cases can also be interesting. So just any possible variation that you can think of here is now sort of possible with this extra switch.